In this video, I'm going to go over the basic differences between the empirical rule and Chebyshev's rule. In the empirical rule, we can apply it when the data is mostly symmetric. So here you'll see a bell curve. Right in the middle, in this light shaded pink area, is the mean. So first the mean has to be calculated. And then you'll see to the left, -1 SD. That means one standard deviation to the left of the mean. The -2 SD is 2 standard deviations to the left of the mean, or below the mean. And this continues down to -4 standard deviations. I usually only see it down to 3 standard deviations. Going to the right of the mean, we have the positive 1, 2, 3, and 4 standard deviations above the mean. Now let's take a look at these shaded areas. In the middle shaded area, we have the values 34.1. Those shaded areas occur when we are 1 standard deviation below or 1 standard deviation above the mean. If we add these data values together, we have 68.2%. What that means is that when we have a symmetric representation of data, that 68.2% of the data should fall within 1 standard deviation below and above the mean. Moving to the peach shaded areas to the left and to the right, we can see that they both have 13.6%. And what I actually want to do is I want to add together all of the percentages that were in the peach shaded area and the light pink shaded area. This represents 2 standard deviations below the mean and 2 standard deviations above the mean. When I add those percentages together, I get 95.4%. That means when you have a symmetric representation of data, you should have about 95% of your data fall within 2 standard deviations of the mean. Lastly, if we go out 3 standard deviations from the mean, and we add up those data values, we change from 95.4% to 99.6%, so almost all the data. So we would say 99.6% of the data, when we have a symmetric distribution, should be 99.6% of the whole data set. Now, this is with a symmetric graph. So I'm going to move now to Chebyshev's inequality. We don't frequently use Chebyshev's inequality, but it's useful to know. Chebyshev's is used when the distribution is asymmetric, not symmetric. So if you have something skewed left or right, or not symmetric at all, here in this example, I do have data that seems somewhat right-tailed. There is some symmetry going on. With Chebyshev's inequality, if we are interested in the percentage of data spread out from the mean, and we could say, let's let the variable k represent the number of standard deviations from the mean. One criteria, though, is that k must be greater than 1. So if I have k greater than 1, let's say 2 or 3 or 4, then I can use this formula to predict the percentage of data that should lie between those different standard deviations of the mean. So k is representing the number of standard deviations from the mean, and I plug it into the formula, and out cranks a number. Looking at the graph, we have these horizontal percentages of at least 75% and at least 88.89%. This at least 75% represents data that is at least 2 standard deviations from the mean. So at least 75% of the data should fall within 2 standard deviations of the mean if we use Chebyshev's inequality. If we go out 3 standard deviations from the mean, then at least 89.89% of the data should fall within 3 standard deviations of the mean. Notice these values are a little less than when we have a symmetric graph and we can use the empirical rule. but it is a great benchmark for knowing that, well, when we're 2 standard deviations from the mean, at least 75% of the data should be there. And when we're within 3 standard deviations of the mean, almost 90%, 88.89% of the data should be within that 3 standard deviations. Just in case you want to see a calculation with this, let's just say I wanted to have k equal 2. Remember, k equals 2 represents 2 standard deviations from the mean. I would take the formula and substitute in the value of 2. So I would have 1 minus 1 over 2 squared, and I'm multiplying this by 100%, just to change it to a percentage. This would simplify to 1 minus 1/4, and 1 minus 1/4 is 3/4. 3/4 of 100% is 75%. This verifies that within 2 standard deviations of the mean, there should be at least 75% of the data.